Hello, everyone. Welcome. Hi, I'm Oliver.
Hi, I'm Lily.
Welcome to Science in Easy English.
Is there an ocean on Jupiter's moon?
So imagine like an ocean that is so incredibly vast, it holds twice the volume of water of all Earth's oceans combined.
Right, which is just a staggering amount of water.
It really is. Now imagine that entire global ocean is just trapped in absolute eternal darkness. Like it's locked beneath maybe 15 miles of solid radiation blasted ice, orbiting a gas giant over 400 million miles from the sun.
Yeah, that is the reality of Europa.
Exactly. So our mission for this deep dive is to explore whether this frozen, seemingly hostile rock is, well, actually hiding a habitable biosphere right beneath its shell.
And to understand the mechanics of that hidden ocean, we're really synthesizing decades of observational data with the absolute cutting edge of planetary science today.
Right, because we have a lot of different sources for this deep dive, don't we?
We do. We're pulling from the legacy data of NASA's Galileo mission, integrating the newest lithospheric modeling from the Lunar and Planetary Science Conference, and of course, tracking the real-time progress of the newly launched Europa Clipper and the European Space Agency's GEOIC mission.
Which are both just incredible missions.
They really are. And the goal here is to get past all the, science fiction speculation and really look at the hard physics and chemistry dictating the conditions inside this moon.
Yeah, and the reason this deep dive matters to you, the listener, is that finding even just like microbial life on Europa fundamentally rewrites biology.
Absolutely.
I mean, it proves that the origin of life isn't some miraculous anomaly requiring a perfect Earth-like surface, right? It would show it's a universal imperative that can take hold anywhere there's water, energy, and the right chemical gradients.
Exactly. But before we get to alien microbes, we really have to establish the physical architecture of the moon itself.
Yeah, because the surface temperature is hundreds of degrees below zero, right? The ice is literally harder than granite. So how do we even know for sure there is a liquid ocean down there?
Well, the initial realization actually came from this brilliant piece of deductive physics utilizing NASA's Galileo spacecraft back in the late 1990s.
Okay, the 90s, right.
Yeah. So Europa does not possess an intrinsic dynamo. Like it doesn't generate its own magnetic field from a churning molten core like Earth does.
Right, Earth has that liquid iron core spinning around.
Exactly. However, as Galileo orbited through the Jovian system, its magnetometers detected an induced magnetic field emanating from the moon.
Oh, an induced field. Because, wait, Jupiter has that massive, rapidly rotating magnetosphere that's constantly sweeping over Europa, right?
You hit the nail on the head. A moving magnetic field passing over a massive electrically conductive fluid will actually induce an electric current within that fluid.
Oh, wow, okay.
And then that current generates its own secondary magnetic field. So Galileo is essentially picking up the magnetic echo of a global, highly conductive layer.
That's wild. And since solid rock and like pure water ice are terrible conductors, the only logical candidate that fits that specific data is a global ocean of hypersaline liquid water, salty water.
Precisely. That induced field gave us the chemical composition salty water, but observational planetary models gave us the physical dimensions.
Okay, how so?
Well, if Europa were frozen solid all the way down to its rocky mantle, the tidal forces exerted by Jupiter's massive gravity would only stretch the moon's surface by about 1 meter during its orbit.
Like 3 feet. Because a solid sphere is incredibly rigid.
Exactly. But the observational data demonstrates that the surface actually bulges and deforms by roughly 30 meters.
Wait, nearly 100 feet.
Yeah, nearly 100 feet of stretching.
Wow. Which conclusively proves the lithosphere is completely decoupled from the interior. The rigid outer ice shell is physically sliding and flexing and, well, floating on top of a massive liquid layer.
Which naturally leads us to the thermal paradox.
Right, because it's freezing out there.
Yeah, Europa is way too far from the sun to maintain liquid water, and it's too small to have retained enough primordial heat from its formation. So the thermal engine, keeping that ocean liquid over billions of years, is driven entirely by orbital mechanics, specifically something called the Laplace resonance.
Okay, the Laplace resonance. What does that mean for Europa?
Well, Europa is locked in this gravitational dance with two of Jupiter's other massive moons, Io and Ganymede, and they orbit in a strict 1:2 to 4 ratio.
So for every single orbit Ganymede completes, Europa completes exactly 2 and Io completes exactly 4.
Exactly. They continuously align at the exact same points in their orbits.
It reminds me of that analogy from our sources. It's like pushing a child on a swing. If you push out of rhythm, you lose momentum. But if you apply a gravitational tug at the precise apex of the swing over and over, you impart massive amounts of energy into the system.
That's a perfect way to visualize it. These repeated alignments force Europa into a highly eccentric orbit, and that orbital eccentricity dictates the tidal flexing.
The stretching and squeezing.
Right. As Europa swings closer to Jupiter, the gravitational shear intensifies, distorting the moon. As it swings further away, the crust relaxes, so the moon is just constantly being kneaded like dough.
I always think of taking a thick metal paperclip and rapidly bending it back and
Oh
forth.
yeah, the heat.
Yeah, the internal friction generates a tremendous amount of heat right at the stress point. So Europa is experiencing planetary scale internal friction, radiating immense thermal energy up from the rocky mantle to melt the underside of the ice shell.
It is. But there's a fascinating contrast here when we look at its neighbor, Io.
Oh, right, because Io is even closer to Jupiter.
Exactly. It's trapped in that same resonance, and it experiences vastly more tidal heating. I mean, it is the most volcanically active body in the solar system.
Just covered in volcanoes.
Yeah, but data from the Juno spacecraft recently confirmed Io does not have a global subsurface magma ocean.
Wait, really? With all that heat, why not?
The divergence between Europa and Io all comes down to phase density. Magma is less dense than the solid silicate rock it melts from. So when Io's interior melts from all that tidal friction, that buoyant magma rapidly fractures the crust and just erupts onto the surface.
Ah, so it evacuates the heat way too quickly to pool into a stable subterranean layer.
Precisely. But water possesses this really rare physical property of being denser in its liquid phase than its solid phase.
Oh, right. Ice floats.
Exactly. So when Europa's tidal heating melts the interior ice, that dense liquid water sinks and pools, while the lighter ice acts as a buoyant insulating lid.
Wow. So the physics of water naturally traps the ocean, allowing Europa to maintain a liquid volume twice that of Earth.
Yeah, it's quite elegant. So now we have a stable, long-lasting ocean and a constant source of thermal energy. But astrobiology requires more than just a warm bath.
Right. Life needs fuel.
Exactly. A biosphere requires chemical disequilibrium, basically a continuous supply of oxidants and reductants reacting to provide metabolic energy. And we know the surface of Europa is constantly bombarded by Jupiter's intense radiation belts.
Which sounds bad for life.
On the surface, yes. This radiation acts as a particle accelerator, bombarding the surface ice, breaking the H2O molecular bonds, and synthesizing highly reactive oxidants like hydrogen peroxide and free oxygen.
Okay, but this is where I run into a massive logical hurdle with our sources.
Let's hear it.
Well, the physical models estimate that the ice shell is between 12 and 15 miles thick. That's like 20 kilometers of solid cryogenic ice acting as a vault door.
It is a formidable barrier.
Right, so if you have radiation generating life-sustaining oxidants on the absolute surface and the water is 15 miles straight down, they are completely isolated. It sounds like the ocean is trapped in a sealed container. Like, how does the chemical fuel on the surface ever reach the thermodynamic engine at the bottom?
Yeah, that's a great question. And that paradox has actually been the primary bottleneck in Europa habitability models for a decade. It's called the stagnant lid problem.
Stagnant lid, yeah, that makes sense.
But there's a recent really fascinating study published in the Planetary Science Journal by Austin Green and Catherine Cooper, and they propose a mechanism called crustal delamination.
Crustal delamination.
Right. They argue the ice shell is not just a static monolith. The uppermost layer is brittle, extremely cold, and loaded with heavy salts and those radiation-synthesized oxidants.
Okay.
But the ice beneath it, closer to the ocean, is warmer, much more ductile, and less dense.
Oh, I see where this is going. So you have a heavy, dense layer sitting directly on top of a lighter, softer layer.
Exactly.
That is a textbook really Taylor instability. Like, gravity is definitely going to try to correct that inversion.
Yeah. And Green and Cooper's thermodynamic modeling shows exactly how it corrects. Plumes of warm, ductile ice slowly rise toward the surface, while massive chunks of the cold, dense, oxidant-rich surface crust mechanically break off or delaminate and just sink vertically downward through the warmer ice shell.
Wow, so it acts like a planetary scale lava lamp, slowly churning those surface oxidants all the way down to feed the ocean below.
Yes. It fundamentally solves the top-down delivery problem. The ice isn't just migrating horizontally via tectonic spreading, it is actively transporting chemicals vertically.
That is incredible. And actually, the sources mentioned we should probably expand our definition of the habitable zone to include the ice shell itself, right?
Okay.
Because there's a structural difference between congelation ice, which freezes slowly and solidly right at the ocean boundary, and frizil ice, which forms rapidly in supercooled, turbulent water, creating this looser, slush-like matrix.
Right, and within that Brazil ice matrix, you find these things called brine pockets. As the seawater freezes, it actually expels the heavy salts, creating these highly concentrated liquid microenvironments trapped within the solid ice structure.
And we see that on Earth, don't we?
We do. We see complex microbial communities thriving in identical brine pockets within Earth's Antarctic sea ice. So as those delaminating blocks of oxidant-rich ice sink, they could be interacting with these brine pockets, creating isolated vertical ecosystems miles above the actual ocean.
Okay, so the top-down delivery of oxidants is highly viable, but biochemistry requires an electron donor to complete the circuit. We need reductance compounds like hydrogen or methane from the seafloor to react with that descending oxygen.
Right, the bottom-up part of the equation.
Exactly. And on Earth, we found the perfect optimistic analog back in 1977 on the Galapagos Rift, right?
Oh, the hydrothermal vents.
Yes. Hydrothermal vent ecosystems thriving in pitch blackness, fueled entirely by the chemical energy billowing out of the tectonically active seafloor. Could Europa have these?
Well, hydrothermal vents have been the gold standard for astrobiological models for a long time. But we have to look at the conflicting evidence. There was a highly scrutinized and frankly pessimistic study led by planetary scientist Paul Byrne at the 2024 Lunar and Planetary Science Conference.
Okay. What did they find?
His team ran complex computer modeling of Europa's lithosphere, the seafloor rock, taking into account the immense hydrostatic pressure of a 100-kilometer deep ocean pressing down on a relatively small planetary body.
The pressure down there must be astronomical, like compressing the seafloor rock and dramatically increasing the melting temperature of the mantle.
Exactly. And the models indicate the rock is simply too strong and rigid. The internal heat generation, while it's enough to melt ice, might not be sufficient to melt silicate rock under that kind of intense pressure.
Oh, wow.
Because Europa has been cooling for billions of years, the mantle may be completely locked. Magma cannot escape to fracture the lithosphere. The conclusion of that study is that large-scale active volcanism and hydrothermal venting might just be physically impossible today.
Man, that's a bummer. It's the equivalent of a pot of soup on a stove where the burner was shut off like 2 billion years ago.
Yeah.
The liquid is still there, insulated by the lid, but there's absolutely nothing cooking at the bottom.
That's a very vivid way to put it, yeah.
But wait, if the seafloor is dead, doesn't that cut off the supply of reductants? Does that mean no life?
Not necessarily.
Mm.
The jury is really still out on this. When you synthesize these conflicting studies, it relies on low-temperature geochemical reactions.
Oh, so you don't need magma.
Right. You do not strictly need a magma-driven hydrothermal vent to produce reductants.
Yeah.
You simply need water circulating through fresh fractures in ultramafic rocks, like olivine.
Okay.
This process is known as serpentinization. It chemically alters the rock, incorporating the water into the mineral structure and releasing significant amounts of heat and hydrogen gas as a byproduct.
Ah. And hydrogen is the perfect metabolic fuel for methanogenesis. So even if the core isn't spewing giant plumes of magma, the tidal flexing we talked about earlier could be constantly microfracturing the cold seafloor rock. right? Allowing water to seep in, drive that serpentinization, and just steadily bleed hydrogen into the deep ocean.
Exactly. So the critical variable we are left with is figuring out the overarching chemical gradient of the ocean.
Right, the balance.
Yes. Is the environment overwhelmingly oxidized from all that crustal delamination? Is it highly reduced from the seafloor serpentinization?
Mhm.
Or, ideally, does it sit in an optimal balanced state somewhere in the middle where microbes can exploit the gradient between the two?
Which is the million-dollar question. But, you can only run so many computer models before you hit the limit of theoretical physics.
Very true.
To answer the gradient question, we actually have to send the hardware, and we are currently doing exactly that.
Yes, the cavalry's arrived.
Literally. NASA's Europa Clipper successfully launched in October 2024, and ESA's JUICE mission launched in 2023. Clipper is currently utilizing gravity assists from Mars and Earth to build the massive velocity needed to reach Jupiter by 2030.
And the mission architecture for Clipper is just a masterpiece of orbital engineering. It's important to note, it is not a lander. It isn't looking for alien fish swimming around.
Right, it's an orbiter.
Well, technically it orbits Jupiter, not Europa,
Yeah.
to survive the radiation, but it is designed to rigorously assess habitability. To survive Jupiter's lethal radiation belt, Clipper will perform 45 distinct flybys, plunging into the radiation zone, sweeping mere miles above Europa's surface to gather dense packets of telemetry, and then zipping back out to safety to transmit the data.
The instrumentation payload on that thing is staggering. Let's look at the Reason radar.
Oh, Reason is fantastic.
Instead of relying on optical cameras that can only see the bright white surface, Reason uses dual-frequency radio waves, VHF and HF bands to penetrate deep into the ice shell.
Right. It measures the dielectric contrast within the ice. So as the radio waves travel downward, they reflect off boundaries where the density or composition changes.
Like hitting a brine pocket.
Exactly. Like a transition from solid ice to a liquid brine pocket, or that ultimate boundary where the ice shell finally meets the ocean. By mapping those reflections, Reason will give us a three-dimensional tomographic model of the entire ice shell. We will finally see the crustal delamination in action.
That is going to be so cool to see. And complementing the radar is the Surface Dust Analyzer, or SUDE.
Yes, SUDE is brilliant.
Because Europa is constantly bombarded by micrometeorites, right? So surface material is continually ejected into the moon's exosphere. And furthermore, if there are active plumes venting ocean water straight through the ice, SUD will fly directly through them.
And SUDE utilizes time-of-flight mass spectrometry. It physically scoops up those ejected ice grains and measures their atomic mass, instantly identifying the specific organic molecules, salts, and isotopes within them.
So we can directly analyze the chemical composition of the subterranean ocean without ever having to drill a single hole through 15 miles of ice.
Precisely. And Clipper is also carrying next-generation magnetometers and gravity sensors.
Right, to map the ocean.
Yes. By precisely measuring the Doppler shift of the spacecraft's radio signal as it gets tugged by Europa's gravity, and by tracking the variations in that induced magnetic field we discussed earlier, we will map the exact depth, global volume, and salinity of the ocean.
And what's incredible is that we don't even have to wait until 2030 to know the hardware is sound.
Oh, the early calibration data.
Yeah. Early telemetry from Clipper's post-launch calibration passes confirms the magnetometers are operating flawlessly. They are successfully filtering out the magnetic background noise of the spacecraft itself and are perfectly tuned to capture those subtle magnetic signatures required to profile the ocean. The tools are absolutely ready.
They are. And the data we receive in the 2030s will undoubtedly challenge everything we think we know. I mean, if Clipper confirms the ocean possesses the right chemical gradients, it entirely dismantles the classic habitable ozone theory.
Right, the old Goldilocks zone.
Exactly. The assumption that a biosphere requires a rocky planet situated at the exact optical distance from a star to maintain surface water.
It just proves that stellar heat is completely optional. If tidal forces in radiation-driven surface chemistry can sustain a biosphere beneath the ice, then the universe is suddenly overflowing with viable real estate.
It really is.
Just looking at our immediate cosmic neighborhood, we have Saturn's moons, Enceladus and Titan, Jupiter's Ganymede and Callisto, and even Pluto harboring subsurface oceans. The probability equations for extraterrestrial life just go exponential.
It's thrilling. It forces us to view these icy worlds not as frozen tombs, but as planetary-scale incubators.
And that leads to a really profound philosophical shift, I think, for the listener to mull over. When you look at images of Europa, it is so easy to see a desolate, incredibly hostile wasteland bathed in lethal radiation.
It certainly looks that way.
But think about the functional utility of a 15-mile thick shell of solid ice. It is the ultimate planetary armor.
Oh, absolutely.
It completely shields the ocean from the sterilizing radiation belts. It absorbs the kinetic energy of extinction-level asteroid impacts. It entirely isolates the biosphere from the chaotic climate shifts and stellar flares that continuously threaten surface-dwelling organisms on planets like, well, Earth.
Right. By locking the ocean away, the ice guarantees billions of years of absolute thermodynamic and chemical stability.
Exactly. So the environment we initially judged to be the most hostile to life might actually be the single most secure, protected, and stable sanctuary in the solar system. Just a quiet, dark ocean where life has had 4 billion uninterrupted years to figure out how to thrive.
It is a phenomenal perspective, and one we are finally on the verge of testing. Thank you for joining us as we unpack the mechanics of Europa.
Keep questioning the data, and we will catch you on the next deep dive. Goodbye.